Hi, this video is on the inverse of a matrix. If you understand well what the inverse of a number is, it should be easy to understand what the inverse of a matrix is. So we'll say, for example, that a half is the inverse of 2 because when I multiply the two together, whether I write a half times 2 or 2 times a half, I get back 1, and 1 is the neutral element of real number multiplication. So multiplying any number by 1 gives you back that number. Well, for matrices, it's kind of the same thing. If A is a square n by n matrix, we'll say that B, also n by n, is its inverse if A times B is the same as BA, which is the same as the identity matrix, and I is going to be, in this case, n by n. So most of the time we write I, since the number of rows and columns are the same, as in only. So that's the matrix. If you'll remember from the other week, it's the matrix which has ones on the main diagonal and zeros elsewhere. Okay. If we can find a matrix P which satisfies the two equations, or two equations, right? It's AB equals I, BA is also equal to I. So if there's such a matrix P, if matrix B exists, then we say that B is the inverse of A. Now for real numbers, the only number that doesn't have an inverse is the number 0. But for matrices, it's more complicated. There are matrices that have non-zero entries, even though they're not invertible. There's no matrix P that you can multiply them by so that you end up with the identity matrix. So the notation we're going to adopt is the same notation we use for real numbers. So a half is the inverse of 2, and we can write a half as 2 to the minus 1, right? So we're going to write the same thing for the inverse of a matrix. We're going to say that B, if it exists, it's A to the minus 1. So that's the notation for the inverse of a matrix. So this way, we can write A times A inverse is equal to inverse times A, which is the matrix I. So this way, using this notation, we can also use the properties of exponents with matrices, just like we use them with real numbers. So A is like A to the 1, this is A to the minus 1. We can actually multiply them and end up with a matrix A with an exponent that is the sum of those two exponents. So we can write 0 here. So we'll say that A to the 0 is the identity matrix. So this way, we can write something like A to the 2 times A to the minus 1 times, I don't know, A to the 3 equals to, if I add the exponents, that's A to the 4, okay? Which is the same as A multiplied 4 times by itself. Okay, we'll also give meanings, but we're not ready yet to something like A to the minus 2, okay? So we don't know what that is right now. One thing that is also true is that the inverse of a matrix is unique. So we could possibly think that for a given matrix, there's multiple matrices that will end up being the inverse, but that's actually not true. So if we have one inverse, it's the inverse of the matrix. So we're always going to refer to the inverse of the matrix and not an inverse, okay? And there's a proof for that. I'll ask you to read it in the book. The inverse of a matrix is unique. So this is theorem 1.4.4 I believe on page 44. Okay, so I'd like you to read the read the proof. And maybe just to finish, I'll show you an example of a matrix that is invertible. So let's say A is 1, 2, 1, 3, and so I could write say, and let B be the matrix 3 minus 2 minus 1, 1. Okay, then let's verify that B is the inverse of A. And the way we want to verify this is by making sure that the two equalities I have on this line are verified. So I need to verify that AB is the same as BA, and that's the same thing as I. So let's do that. AB, well, that's 1, 2, 1, 3 times 3 minus 2 minus 1, 1. If you multiply them together, do it, you'll see that you get 1, 0, 0, 1. So you get I2 as expected. Okay, if you do B times A, you can verify that you also get I2. Okay, so we can say that A inverse, which you also can write like that, is the matrix B. Okay, more in the next video.